Take a look at this massive white commercial airplane suspended against the clouds. It's a sight so common we barely even register it anymore. But consider the sheer weight involved. A single human being has no biological equipment to fly, yet we've engineered machines weighing over 700,000 pounds, the equivalent of 5,000 adults, and we routinely hurl them into the stratosphere. Every single ounce of that immense mass is under the constant downward influence of gravity. To understand how we overcome that weight, we have to look at the atmosphere differently. At the speeds required for flight, air stops behaving like empty space and begins to act like a heavy, tangible, physical substance. An airplane doesn't move through a void. It travels through an ocean of atmospheric fluid. When a dense, fast-moving object interacts with that fluid, it creates intense, opposing physical forces. Keeping those hundreds of tons in the air is a matter of a strict mathematical equation. It requires balancing 4 specific physical forces against one another in real time. The first force is weight. This is the literal gravitational pull drawing that 700,000-pound mass toward the ground. To counter that weight, we use lift. This force is generated entirely by the specialized curved shape of the airplane's wings, known as an airfoil. You can see the effect in this cross-section. As the wing moves forward, it physically squeezes the air at its leading edge. Because of the curve, air over the top travels faster, creating low pressure. Meanwhile, slower air underneath creates high pressure. This pressure differential creates an upward push from the air below the wing, providing the physical support necessary to keep the aircraft from falling. However, this lift only exists if the plane is constantly forcing high-speed air over the surface of its wings. As the plane pushes forward to generate that speed, it encounters the third force, drag. This is the air resistance and friction that pushes back against the aircraft's motion. To overcome that resistance, we need the final force, thrust. This represents the mechanical power required to move the plane forward through the atmosphere. This is achieved through the complexity of the jet engine. It pulls atmospheric air through these internal turbine blades, mixes it with fuel, and blasts it backward at high velocity. When the engine's thrust exceeds the atmosphere's drag, and the wing's lift exceeds the plane's weight, the aircraft stops being a ground-bound object and begins to climb. Every second of a flight is an active tug-of-war, requiring the constant maintenance of these 4 forces. Aeronautical engineers are constantly refining this balance. For example, this subscale NASA research aircraft allows scientists to test new aerodynamic configurations without the risks associated with full-size prototypes. This research is now being applied to develop ultra-efficient green aviation and autonomous urban air taxi networks. We can see the evolution of these designs in the NASA X-59. Its elongated nose is specifically shaped to pierce the air at supersonic speeds, while minimizing the shockwaves that usually cause loud sonic booms. Looking up at a plane today means seeing a delicate physical balance in motion, the result of precise mathematics and constant mechanical adjustments that keep hundreds of tons of metal suspended in the air.